In the previous class, we started with the concept of memory. Like memory is simply a kind of location where your information is going to be saved. And also we have seen various types of memories like primary memory, secondary memory, tertiary memory, and various kind of examples along with the hierarchy of the memory system, right? So which one is going to be very cost and which one is going to perform more performance, right? So in addition to this, we have seen the structure of magnetic disk, right? So means if I take any kind of a disk, this disk is a collection of various kind of plotters, and each plotter contains a collection of tracks, and each track contains various kind of sectors, and this sector contains a data. This data will be depend on the density of the location, right? Means they will clearly define how much is the density for per centimeter, right? Meaning that how much amount of data that they can able to save per centimeter. Like that, they are going to specifically define that thing. Technically, we can call it as density. Meaning that, for example, if I say density in other words as like 2048 bits per centimeter, this is the density. What is the meaning of this one? For a particular location, the density, for example, if I say for a particular location means if I say the location space is 4 centimeters, the density is 2048 bits per centimeters. Means for 4 centimeters, how much amount of memory I can able to save? Some into 2048 into 4, right? This much amount of bits I can able to save in the respective location. This is what I can call it as density, right? Density we can able to define simply in terms of per centimeter, how much amount of bits I can able to save, right? So, and also we have seen some kind of problems regarding that magnetic disk, right? So this is what we have seen. Now in today's class, we'll see further. I mean, if you are going to take any kind of a memory, this memory can be any kind of a RAM, or it can be a kind of a ROM also, right? If you look into any kind of a ROM, this ROM can able to store some data, some files. Like for example, if I say A and B are the two files can be saved by this ROM, right? Now if somebody wants to access this hard disk, single person, yes, it is perfect, there is no problem. But if multiple people are accessing, like lakhs of people are accessing from the same single disk, what about the read performance? Is going to be decreased or not? Like if you observe something like manabadi.com, right? So when you are trying to access your 10th class results, so they are going to provide 2 or 3 servers. Why they are going to provide 2 or 3 servers instead of only one server? Because reading capacity is going to be decreased for the server, right? Meaning that when concurrent accessing is going to be happen on the single server, definitely its performance is going to be decreased. In order to avoid performance issues of the server, they are going to maintain multiple parallel disks, right? So that is what, based on that example, I can say that when you are going to have a single disk, read performance is going to be decreased when multiple people are going to be accessed concurrently. Am I right or not? For that reason, what I can do, can I make use of splitting this single disk into multiple disks? I mean, not this same disk. I am going to use multiple disks. I am going to stripe the data into multiple disks, right? If I am going to have 2 files, one file is placed in one disk, another file is placed in one disk, right? For all the people who belongs to AP, I am going to relate to this server. For all the people who belongs to Telangana, I am going to relate to this server, right? So at that time, your like read performance is going to be, it cannot be decreased, it can be constant also, right? So meaning that there is no effect on the read performance because I have divided the traffic into 2 servers, right? So this kind of mechanism I can call it as data striping. Data striping, simply I am going to distribute my data into multiple disks. That one I can call it as data striping, right? Yes. Now here the question is, for example, if my disk is failed, is there any chance to get back the data? No, it is not possible. Why it is not possible? Because I haven't maintained anyway. Is there any solution for it? For example, I am going to have a disk contains A and B. I am not thinking about like read performance. I am thinking about now if the disk is failed, what will happen? Right? If assume that this is a kind of thing. If it is going to be crashed, my data is going to be lost. Instead of that, what might be the solution? Can I make use of same copy of data in another disk? If I maintain, even if this disk is going to be failed, definitely I can able to get it from the another disk, right? So what about the reliability of this design now? Reliability means what? Even if the system crashes, even any kind of situation, your database should not lose your data, right? So reliability is increased or not here. But whereas coming to earlier case, reliability is 0. Why reliability is 0? We are not making any duplicate data. If it is going to be lost, definitely we are going to lose. But coming to this particular scenario, reliability is increased, right? So this thing I can technically call it as mirroring. Mirroring means simply a duplicate of data. When you are going to maintain the mirroring, definitely you can able to achieve the reliability of the disk. I cannot able to lose its data even if any disk is going to be failed. Again the question is, you may get, even if this disk is failed, then obviously reliability is going to be 0. We cannot expect all the situations, right? But we may expect that there is at least a chance of losing one particular disk. So we are going to maintain simply another temporary disk. So based on these 2 points of data striping and mirroring, they come up with one concept called RAID mode. RAID. So RAID means redundant array of independent disks. Redundant array of independent disks. The name itself is clearly providing. It's a kind of a technique which is meant for to improve the performance, I can say technically, to improve the read performance and to improve the reliability. We are moving for some set of specific kind of technologies. We call them as collectively as RAID, redundant array of independent. The name itself is clearly understood here. It contains the redundant data. Array means collection, and all are going to be independent. Redundant array of independent disks. That's it. In that collection of independent disks, where it may contain redundant data also. Right. So among those, one kind of technique I can call it as RAID level 0. So based upon the way they are following the techniques, they name it different ways. One is RAID level 0, which doesn't contain any redundancy. We can say it doesn't contain any redundancy. Right? When there is no redundancy, what about the reliability of this particular kind of database structure? What about reliability? Is it high or is it 0? Reliability is 0. Why is it 0? For example, if I say the data is something like A, B, C, D, E, F, I am going to have 2 disks. One is A, B, C, D, E, F. Right? Now, if the first disk is going to be failed, this is disk 1, this is disk 2. If first disk is going to be failed, can you able to get back it? I haven't saved, so I cannot able to get back. So it is reliability 0. Simply I can say that reliability follows a technique of what? Data striping. So as I am applying the data striping technique, what about the read performance? Increases. Is there any burden on the write performance? I am going to simply write on multiple disks. That's wherever it is free, I can just simply write. So there is no problem for the write performance. It is as usual, as normal. Right? What about the utilization of the space? I can say generally effective utilization of the space. Is there any wastage of the space here? So effective utilization of the space is 100%. Meaning that how much amount of memory is available, that much amount of memory I can definitely use. That is what the meaning of effective utilization of the space is 100%. Right? So the problem here is reliability. Right? When the particular system is going to be crashed, definitely my database cannot able to handle to recover the data. So we are moving for another kind of RAID level, that is RAID level 1. RAID level 1, right? So in RAID level 1, they are not thinking about the performance of the reading, they are going to think about the reliability, right? So as they are going to think about the reliability, they are saying that this technique contains the mirroring. Yes, we are saying that it is mirroring. If I am going to have one disk which contains the data as A, B, C, D, E, F, C. This data I am trying to write. B, C, D, E, F. The same thing it is going to be mirrored in another disk also. So this is what mirroring. Now what about the reliability? Reliability is 100%. If one disk is failed, if another disk also fails, reliability again 0. We cannot expect that situation. But at the best case, if one disk is failed, we can able to get it from the another disk also, right? And what about the read performance? Is going to be increased? No, it is going to be increased, right? I can able to access it from multiple locations. I can able to access from the disk 1 or I can able to access from the disk 2. What about the write performance? Is it normal or is it going to be decreased? It is going to be decreases, because if I write certain data, like J here, definitely I have to compulsory maintain the same copy of data in other location also. So compulsory I have to write it in the 2 locations. So that is why write performance is going to be decreased. Okay, fine. And what about the effective utilization of the space? How much space I am using here? Half of the space I am wasting to maintain the redundant copy of data. So I can say it is 50% of the effective utilization of the space. See, I mean, if I am going to have n disk, where each disk contains B blocks, then effective utilization of the space is n into B by 2. Whereas coming to here in RAID level 0, n into B, where n is number of disk, B means number of blocks in each disk. Okay, now next, coming to another kind of RAID level. So the technical term as 0 plus 1. What is the meaning of this one? They are simply combining mirroring along with data striping, right? So we can say it is a combination of data striping and mirroring, so that we can able to reduce the drawbacks of RAID level 1 and drawbacks of RAID level 0. We can get some new kind of mechanism, right? So here whatever data that you are going to have, that is going to be distributed A, B, C, and we are trying to apply the mirroring, right? So A, B, C, D, F, and more thing is D, F. All are going to be connected. Now here we are going to achieve the reliability. Reliability is high, and we can able to improve the read operation also, and write operation anyway decreases. What about effective space utilization, which is n into B by 2, right? Because we are simply making use of the entire content duplicating. So that's why half the memory is going to be completely wasted. Okay, now. So next kind of level, that is RAID level 2, which we can call it as, what happens? RAID level 2, which they are mainly concentrating on error correction and error detection. error correction and error detection, right? So basically, so mainly when you are going to work your database with respect to this kind of technique, your database always going to find out various kind of errors, and if there is any kind of error, it can able to identify those errors also, right? So basically, if you would like to find out 1 bit errors, definitely you can able to use the concept of Hamming code, right? Hope you have the idea of Hamming codes, right? So if you would like to send 4 bits of data, if you would like to send the 4 bits of data, how many parity bits are required? 3 parity bits are required, right? If I would like to have a maximum of 11 bits, I have to use 4 parity bits. If I am going to have 25 bits, maximum of I can able to use 5 parity bits. I mean, if I say, if I would like to store 4 bits of data, 4 bits of data, how many disks I need? I need 7 bits. I need 7 bits. Why? For example, 1 0 1 1 I would like to send, and these 3 are what? These 3 are meant for the parity. Meant for the parity mode, right? So in your terminal it will be like P1, P2, I think P4, right? D0, D3, D5 and D6, right? You can able to calculate it and you can get the answers, right? So this is what the RAID level 2 mechanism, right? If you are able to observe here, what about the effective utilization means? It will be like 4 by 7. The reliability is, sorry, it should not be reliability, it is like effective utilization of the space is 4. Actually, I need to store only 4 bits. I need to store only 4 bits. But how much memory I am wasting? Extra 3 bits, right? So effective utilization is 4 by 7%, right? Here what is effective utilization? 11 by 15. Here what will be the answer? 25 by 30 is the effective utilization, right? Meaning that as number of bits storing is more, effective utilization is going to be, effective utilization of the space is also going to be increasing in RAID level 2. Meaning that when you are going to have vast data and trying to work for error correction detection, then you can go for RAID level 2. Okay. So coming to next kind of level, that is RAID level 3, which we can call it as bit interleaved parity bit, right? In the earlier case, what happened here? We are trying to save your parity data in multiple disks. Instead of that, why can't we go for only single parity, right? That single parity can be either an even parity or it can be an odd parity, right? Meaning that if I am going to have 4 bits, if I am going to have 4 bits, how many parity bits we are going to require? Only 1 parity. Why? We are simply using either even or odd, right? If I say, right, is all are going to be connected. If I say 1 0 1 1, if I say it is even parity, what will be this value? 1. To make this as even parity, right? So number of ones are odd, so to make it even, I have added one more one. So this is what parity disk. I am going to separately maintain one parity disk, separate disk, so that I can able to maintain. For example, if I am going to, if this disk is crashed, can I able to get back whatever the data that is available in this disk? According to this example, yes, because it is 1 0 1 1. Number of ones are even, so I can able to guess the answer here as 1. This is what RAID level 3 is defined. And simply I can say it has bit interleaved parity bit. Coming to RAID level 4, we can say it as block interleaved parity bit. Block interleaved parity bit, right? So in block interleaved parity bit, instead of distributing data, here 1 0 1 1 data is distributed over the multiple disks. Here we are not distributing. Whatever data that we are going to have, the data entirely saving in the same disk only. 1 0 1 1 1 1 0 0 1 1 1 00 or 0, and last bit again anyway it will be a kind of parity bit only. For all these things we can able to calculate the parity and we can able to define the answer. But anyway every rate technique have its own drawbacks, its own advantages, right? So this particular thing having the drawback is what? If data is modified, even it is not crashed, data is modified, definitely you are going to lose our data. Why? See, if I say that total number of ones are here 1 2 3 4, assume that this is 1 0 0 4 4 8 9, right? If I say here it is 1, it is 1 or 0 3 4 8 9. So to make it even I have to place here 1, right? Now for example, if this data is crossed and modified as 0 1 0 0, at this point of time can it able to identify? No, it couldn't able to identify, right? So it's only having its own drawbacks, but there are certain situations we can able to use this kind of technique also. And coming to one more RAID level, RAID level 5, which is block interleaved distributed parity bit. What is the meaning of this one is, instead of placing the parity bit at one disk, instead of always maintaining the parity bit at one disk, try to distribute over multiple disks, right? Distribute over multiple disks, right? So 1 0 0 something like parity 1, and 0 1 parity 2 0, 1 parity 3 0 1, P4 something like 0 0 1, something like this, right? So meaning that instead of maintaining at one disk, try to distribute over the entire disk. That mechanism we can call it as RAID level 5. And coming to the final level, that is RAID level 6, which they are saying that if a particular parity bit is lost, the particular parity bit is modified, or particular parity bit disk is lost, how can we compute? We need to have to compute, right? We need to have to compute again, right? For example, if I say 0 1, what is this value here? To make it even, I have to place the value as 1. I have to place the value as 1, right? Now assume that this disk is crashed. I want to get this data. What I have to do? I have to first compute entire thing, and then only I can get the answer. Right? But the situation here is, instead of making the compute, instead of calculating again, what they are saying is, we can able to simply use block interleaved distributed two parity bits. Block interleaved distributed two parity bits. What does the meaning as one? Same parity bit you are going to maintain at two locations, right? If I say 1 0 0 P1, same I am writing 0 1 P2 0, 1 P3 0 1, P4 0 0 1, 0 0 1. Here I am trying to maintain something like P1. Here I am trying to write something like P2, which will be 0, something like P3. I am assuming that P4 and this will be 0, right? Meaning that if this particular disk is going to be crashed, if, for example, if as per this example explanation, if this disk is crashed, instead of computing the entire data, what you can do, you can just simply get it from the parity 2. So what is the parity 2 here? Here it is already 1. It's already 1. Why you got here 1? Because this parity 2 is 1, the duplicate is available here. As it is lost, I can get it from this parity 2. So this mechanism they are saying that as block interleaved distributed two parity bits. So this mechanism we can simply call it as RAID technology, right? So many kind of companies are using this one, but as per academics, it's a purely a theoretical concept, right? Next, we'll see one more kind of topic. disk space manager. So guys, basically when your data is going to have in secondary storage device, we can generally call it as hard disk or SDD or whatever it may be, which is available in the ROM. When you are trying to save it from the CPU, right? I would like to save the file. There are certain kind of a person who is taking care of entire this process, right? So we can call them as disk space manager. It's a kind of a software which will take care of allocating and deallocating of the memory space, in the disk, right? So meaning that anyway, your data is going to be stored in the form of a various kind of a disk or various kind of a blocks. Which file need to be placed at which location is going to be defined by disk space manager, right? So which contains all the data, like where the free blocks are available, where the blocks are completely full, which is already known to the disk space manager, so that it will take care of where to load what kind of data. And if somebody is requesting for certain kind of data, how it need to respond will be decided by disk space manager only. Okay, fine. So basically it can follow various kind of allocation strategies. One is a kind of contiguous allocation strategy, right? Meaning that when a particular request is coming to save a particular file, it can save using a concept called contiguous allocation. Another one is you can able to allocate the memory in a linked allocation fashion. These are the two ways you can able to allocate. In contiguous allocation space, if I am going to have a file called j.c file, if assume that this file is of size 20 MB, and if I am going to assume that this is 10 MB, this disk is 1 minute. This particular block is 10 MB, and you might think that all the blocks are of size 10 MB. Then in order to place this j.c file, how many memory locations it required? How many blocks it required? 2 blocks are required. One is 0. Assume that this is 0 index position. 1, 2, 3, 4, 5, 6, 7, 8 and so on. If I am going to assume that its index locations are something like this. If I would like to place this j.c file, how many indexes are required? 2 indexes are required. One is 0 and another one is 1, right? So it is going to maintain, the disk space manager is going to maintain one kind of table where it contains the entire information, which file is available, which location. So j.c file is available at starting location is 0 and its count it is going to maintain as 2. What is the meaning of its count is 2? So how many blocks it occupied from the index portion 0, right? So it is going to occupy 0 and 1. So total 20 MB is available, right? For example, if I say e.c, it is going to have a size of 41 MB. And what is the starting location of this e.c file? Exactly, it is 2, because it is following the mechanism of what? Contiguous memory allocation. Contiguously, after filling one location, it is going to move to the another location. And once a particular block is filled, it cannot able to place another new file. That particular block is completely for only specific file. That's it, right? So it is going to start with the second index portion. And how many blocks it required? According to our explanation, 5 blocks are required, right? 41 MB means you have to allocate 50 MB of memory, right? So it will take up to here. So total how much memory it is going to be wasted here? 9 MB. So this wastage of memory, can I able to use it for another file called k.c file? Assume that it requires something like 9 MB. Can I use it here? No. I have to allocate it in another location called 6 and count is 1 only, right? So now with respect to this one, I can call this e.c file is generating a kind of problem called internal fragmentation problem. What is the meaning of internal fragmentation? Even though even though I am going to have freely available memory location here, I cannot able to use it further. That is what I can call as internal fragmentation. Okay, now, so meaning that free space cannot be usable. Internal fragmentation. Similarly, there is one more kind of word is there. External fragmentation. External fragmentation. This is also possible in contiguous memory location. External fragmentation means even though I am going to have vast amount of memory space is there. Even though I am going to have vast amount of free space is there, I cannot able to accommodate the new file. Right? For example, if I say some 4 blocks are there, each block is occupying assume that 10 MB, each block is having 10 MB, all are occupied 1 MB, 1 MB, 1 MB. So total, how much free space is there here? 36 MB free space is there. My request is, I would like to request to save 13 MB. Right? So this kind of situation I can call it as external fragmentation. Why? So this 13 MB I cannot able to accommodate in one location. But if I am able to combine all the freely available locations, I can able to place. But according to this particular scenario, is it possible to fit this one? No. This is what I can call it as external fragmentation. So these are some of the problems that we are going to face in contiguous memory location. One is internal fragmentation, another one is external fragmentation. And one more thing is, if I say this j.c file, I modified it to some other data. Something like I have added some 10 MB, so which might be 10 MB. Now, is it possible to increase this one? No, it is not possible. Why it is not possible? It is a continuous memory location. So it is already occupied 2 locations. If I would like to place the next location, this should be free. But is it free? No, it is not free. So I cannot able to increase the size of a particular file. So that is also one more drawback here. So I can say it as increasing the file size is not possible. Not possible in contiguous memory locations. Right? So to overcome these drawbacks, some of the drawbacks, we are moving for again a kind of another thing as linked memory allocation. In linked memory allocation, again we are going to have various kind of blocks of data. Right? Here in linked allocation, they are going to use the concept of pointers. If I place j.c file at 0th location, and it is not necessary to place the remaining part of the data in the continuous only. It can able to accommodate some other location. This is one now for this one. Right? Now, if I place e.c file started with this particular location, I can able to place the remaining part here. I can place the remaining part here. I can place the remaining part here. I can place the remaining part here. This is what linked allocation. So here the problem is pointers are very complex, and the advantage is here we can able to increase the file size. How can we increase the file size? Because if I increase here, for example, j.c file I increase with 10 MB, what will happen? Can I able to accommodate this link to this one? It is free, right? That is the advantage of this linked allocation. But the drawback is here we are going to use the concept of pointers. And one more advantage is here fragmentation is very less. Fragmentation is cannot able to completely eradicate it, but it will be very less. Why it will be very less? What is the chance of very less? For example, if I say this particular location is having the 10 MB and it is having the 2 MB, I need to accommodate the remaining 1 MB which is of 40 MB already accommodated. 1 MB I need to accommodate. Which one I can link? I can link with this 2 MB, right? Then I am going to eradicate maximum amount of internal fragmentation or not. So that is the advantage of the linked allocation. For example, try to observe. If my disk is like this, something like 50K of space is occupied already occupied, and 150K is free, 300K is occupied, and 600K is also occupied. Instead of, if I say it is 350K, this is 600K which is occupied already, right? If I say this is a kind of disk, and my new request something like J dot C, E dot C, and K dot C, D dot C, F dot C will look like in this order, right? And each request a size of 300K, 25K, 125K, and 50K. For example, these files I need to save. Now, how your disk space manager will do now? They will try to space these files, right? So, if the first request file is what? J.c. Can I able to place this J.c file in this particular location? Yes, sir. No, it is not possible, right? Because it is free space is 150K. I cannot able to place. So, 300K is going to be placed here. I mean, here J.c is going to be placed. Right? If it is going to be placed, what might be the remaining memory? 50K. Right? Next, E.c came. Right? How can it accommodate? Can I place here to 50K, 25K? Yes or no? Right? So E.c is going to be accommodated, and now 125K is free. 125K is free. Now 125K came with K.c file. So one K.c file is going to be placed. Next, D.c file came. D.c file is going to be placed. So like this, your disk space manager is going to accommodate its data, right? So whatever the procedure that you have seen right now, we can call it as first fit procedure. It's a kind of mechanism, one kind of mechanism disk space manager is going to follow. What we did in first fit mechanism, when a file is coming, whatever that they are coming, they are trying to check for whether I can able to fit at this particular location or not. If it is not, I will move to the next place. If it is not, I am going to move to the next place, and so on. That's it, right? That is what we did, right? So 300K I cannot able to fit in 150. I can able to fit in 350K, yes. And then E.c 25K I can able to fit here, yes. Then 125K I can able to fit the remaining memory space, yes. 50K I can able to fit the remaining space, yes. So this is what you can call simply first fit mechanism. For example, if I say, if you would like to follow another kind of a technique which will fail here in this scenario, observe it is 50K, 300K, this will be 150K, 350K, and it will be 600K. 600K anyway full, 50K full, 300K full already, right? Now observe, I am trying to follow one kind of technique called best fit technique. Best fit. What is the meaning of best fit? I am trying to think about to avoid maximum internal fragmentation. Maximum internal fragmentation. Like, you know, in DA subject, knapsack algorithm is there, right? What is the meaning of this one? You are going to maximize the profit. Maximize the profit means you are trying to avoid the losses of getting the data, right? So best fit means what? If I am going to place a particular item, particular file, I should not lose maximum free space. Maximum free space, right? So that is what we call as best fit. Now in this particular scenario, 300K is going to be placed at which location? Anyway, whether it is what kind of fit, I can able to place only 350K, right? So here J.c file is going to place. The remaining is 50K. 50K. Now 25K come with the file name as E.c. Now where can I place? Is it at 150K or is it 50K? It is best fit, right? Best fit means I need to avoid maximum losses of data. I need to avoid the maximum losses of data, right? So if I place at 150k, 125k is going to be lost. I cannot able to predict the future requirement. But as of now, you have to think that you have to avoid the losses of data. If I place at 150k, you are going to lose 125k of memory, right? So can I place here? Yes, I need to place here only because I am following the best fit technique, right? If I place E dot C here, the remaining is again 25k, right? So best fit technique. And next request is 125k. So 125k where I am going to place, definitely I can able to accommodate here only, that is k dot c. Next remaining is 125k. Remaining space is here 25k. Okay. Next you got the request as 50k with the name d dot c. Now where can I place here? Is it possible to fit 50k? No, it is not possible. So in this particular scenario, best fit is not the correct situation, right? So now you can observe this example will be comes under external fragmentation. External fragmentation. Why it will becomes an external fragmentation? Even though I am going to have enough space which I can able to place the data, I cannot able to place at the two different locations. But if it is a kind of a linked allocation, definitely I can able to place it, right? So this is one kind of a gate question actually. One of the gate question. Okay, fine. So this is what the disk space manager will going to do, right? Which will simply allocate the space to certain requests and which can simply deallocate the files which are allocated based on the need. That's it. Simple one, buffer manager, right? So basically if you are able to observe, if you take any kind of a disk, every time you are trying to take the data from the disk is going to take more time complexity. Am I right or not? Right? Trying to take every time from the disk is going to be more time complexity. So basically if you would like to process it, you are going to have a main memory. Always your data is going to get into the main memory. Then you are going to perform various kind of calculations here. Right? So right, in the last for the decades, they come up with one kind of a technology called cache memory, right? Which I can call it as a buffer also, right? So buffer is a small area which is available in the main memory, where it contains frequently accessed items, right? All the frequently accessed items are going to be available in the buffer, so that when a particular request is coming from anyone, not the CPU, first it will check in the buffer. If it is available in the buffer, then it will directly respond it to the CPU. If it is not available in the buffer, it will check for the main memory. Here if it is available, then it get back into the buffer, then it is going to respond to the CPU. If it is not available in the main memory, then it will request transfer to the disk and it will get back the data, right? So I think in the last class we have explained this one. So this is the general process what is going to be happen, right? So here the task of buffer manager is to decide what kind of files I need to place in the buffer. Will be decided by the buffer manager, right? So for example, if I say try to observe with an example, 1, 2, 3 are the 3 items which are available in the buffer. Now I got the next file names as 1, 2, 3. Assume that all are done. Assume that like this, right? So next in future I am going to think that my requests are coming like this, meaning that I want to save the files as, I need to get the data from the database as 4th file, 1st file, 6th file, 1 file, 5 and 7th files. Now already in the buffer 1 to 3 files are there, but next request is what? Number 4 file. Now my memory size of the buffer is only 1 to 3 files can able to handle. Now what the buffer manager has to do? Buffer manager has to completely replace one of the file, right? what file it is going to replace? Based on the requirement, meaning that the technology or the technique what it is following, right? For example, if it is going to replace it with 1, right? Then next request is what? 1, right? Next what it is going to do? It is going to replace with this one. Next it is going to replace with 6. Next again 1. Is there any need to replace? No, it is already available. No need to replace. So it is done. Next 5 which I need to replace with here 5. Next 7, right? So total here I can say in other terminology as page fault sum. So how many files are fault? Meaning that total how many faults are occurred here? 8 faults occurred. Meaning that 8 times I need to replace it with the buffer of the location. It's not 5. It's like initially entire buffer is free. So buffer doesn't contain first file. So I need to get it first file. I need to get the second file. I need to get third file. Then I need to replace it with the remaining things. Right. So these kind of things are going to be done by the buffer manager. Right. So if you are able to observe, certain kind of other techniques might be there. Something like initially buffer is 0, and irrespective of any kind of technique I am going to follow, definitely I am going to get 1, 2, 3 other files. Now I am going to use least recently used technique. So this kind of technique I can call it as first in first out technique. Whatever the file that I am coming, that will be replaced if it is not there. Right? That is what we did, right? 1, 2, 3 are not there, 1, 2, 3 added. Next 4 came. What is the oldest one? 1. So I replaced with 4. Next I got the request as 1. What is the oldest one from 4 to 3? 2 is the oldest one, right? So 2 replaced with 1. Next I got the request as 6. What is the oldest one from 4, 1, 3? 3 only one, right? So this mechanism I can call it as first in first out mechanism, right? Coming to one more kind of technique, I can say that this is least recently used technique. In least recently used technique, we are going to think about which one I am going to least recently used, right? Meaning that which is not the exact meaning. I can say the another technology as which can follow any kind of technology. Like FIFO or LILO, right? Last in last out, or least recently used, or most recently used, or something like various kind of technologies are there, which you can understood in operating system subject. But as of to touch this concept, I am using some kind of terminology. Right here, to reduce the number of faults. Here, how many faults you occurred here? 8 faults, meaning that 8 times you need to get it data from the main memory. 8 times you need to get data from the main memory, and main memory in turn you need to get it from the hard disk, right? But if you observe, I am going to follow one technique where it may reduce. First 3 faults are occurred. Next I got the number 4. What I did now, I am going to check for the file which I am not going to use in future, right? 4, if you would like to replace with some of the file from 1 to 3, which one I can able to replace? For example, if 2 is also there, which one I can able to replace? Can I replace it with 3? If I replace it with 3, is there any chance of reducing the number of faults or not? Yes, because 3 I cannot able to use in future, right? I can able to reduce. Next I got 1. 1 is already there, no page fault. Next I got 6. Which one I need to replace? 4 only, because 4 I cannot able to use further. Next I got 1, no need to use. Next I got 5. Next I got 7. Next I got 2, right? So if you are able to observe, total how many faults occurred here? 7 faults occurred, right? So this is one kind of scenario where you have reduced the number of page faults. Meaning that what? In order to achieve this requirement to the user, meaning that user is asking for first file, second file, third file, fourth file, first 6, 1, 5, 7, 2 files in this order. if I am going to use this green color technique, what I explained here, is going to request for 7 times of the hard disk. 7 times hard disk. If I am going to use FIFO technique, it is asking for 8 times of the hard disk accessing, right? So this will be decided by buffer manager. This will be decided by buffer manager, right? So we can stop here. So this is the concept of buffer manager.